So, hello guys. Uh, in the beginning, let me just clarify that indeed I work for this small Korean company that manufactures a couple of models of mobile phones, maybe some ships, some tanks and stuff like that. But most of the stuff that I will be talking here are a part of my PhD studies. Indeed, I used to work on USB in Samsung, but now I'm focusing on some other projects. So, some outline for today. In the beginning, I would like to give you some brief introduction to the USB protocol just to ensure that we are all on the same page. Then I will talk a little bit about sniffing the USB traffic and modifying it. And then I will go to some security testing of the USB stack, and we will see if we manage to fit demos in. Okay, so the USB protocol itself, I would say that most of the issues related to the USB and for people who are starting with it is that people believe that there are some dragons inside the protocol. So if you take, for example, the Ethernet stack, it's really well known. A lot of people talk about it during their studies. We have some experience with it. But when you start talking about the USB, people say, no, it has to be hard. It is USB, it has to be hard, it has to be complicated. And most of that issues comes from lack of knowledge how to properly try to sniff something. So if you're unable to sniff the traffic, it's not very easy to debug your application. So this is why you believe that there are dragons inside the protocol. So today I will do my best to show you that there is literally no dragons inside the USB protocol unless we are talking about the USB-C. So that's why I'm not going to talk about it today. So USB protocol, what USB is about? So USB is in general about the same thing as the internet. It's about using and providing a service. In internet world, we have some servers, we have some clients that connect to the server and try to use the service. A single server may provide multiple services, and a single client can connect to multiple servers. In USB world, we've got a USB host, which is usually the machine that is used by the end customer, the human user, and we have number of USB devices connected to that host. A single host may have multiple USB devices connected, but a single USB device may be connected to only a single host at a time. A single USB device may provide one or more services functionalities to the host. So those are the functions that Andrzej mentioned before me, right? But how do we communicate in case if a USB device provide more than one service? So in Ethernet world, we have those ports. We have 65K of ports, so we may have number of applications listening on that ports. In USB, we have up to 31 endpoints, which are mostly the equivalent of the ports from the network world, but the difference is that they can transfer the data only in a single direction. Only endpoint 0 is capable of transferring the data in both directions. All other endpoints are either in, which means that they can transfer the data from device to the host, or they are out, which means that they are capable of transferring the data from host to the device. So we are always saying here from the host perspective, because USB is in general a host-centric bus. If you are talking about different types of transfers that you can use, in internet world, usually you choose between TCP and UDP, depending on your use case. Here we have 4 types of transfer that you can use. The first one is the control one, which is the only one which is bidirectional, reserved for endpoint 0. It is mandatory for every device to implement that kind of transfer, and it can be used. It is used during discovering of the new USB device, but it can be also used later by the application. Unfortunately, it is not very efficient, and the transfer are quite slow compared to other types. The next one is the bulk. This is the one which is the most popular. All the smartphones that you have in your pockets, all the mass storage devices use the bulk transfer. It is used to transfer a large amount of time-insensitive data. So it can be used for transferring network packets, mass storage, and stuff like that. The next one is interrupt. And interrupt is used to transfer a small amount of data which is time-sensitive. And the important thing is that it reserves a bandwidth on a bus and can be used for very time-sensitive applications like human interface. So if you move your mouse, you need to minimize the delay. As we will see later during the talk, interrupt is only a name for that kind of transfer because there is no real interrupts like we know from the hardware. It's only a pooling with a strictly defined interval by the host. The next one is ISO, which is used to transfer a large amount of time-sensitive data, but there is no free lunch. So if you transfer a large amount of data, there is no delivery guarantee. One of the most famous features of USB is so-called plug and play. So you connect your USB device and all the drivers are automatically loaded, everything is automatically configured. In order to be able to implement a feature like this one, you need to have some way of discovering the capabilities of the USB device. That's why a USB standard defines a logic view that can be applied to every USB device in the world. So basically, you have our endpoints, which are here. And endpoints are grouped into interfaces. An interface is a group of endpoints that are used to implement some well-defined, well-sandboxed functionality. Like Andrzej mentioned, the MTP interface, the MTP functionality. The MTP interface is going to have 3 endpoints. 2 of them are bulk, and 1 of them is interrupt for some asynchronous events, right? Interfaces are grouped into configurations, and configuration is a group of interfaces that can be used in the same time. Whole USB device may have multiple configurations, but only one of them can be active at the same time. The only special endpoint that is always available is the endpoint 0. It is not grouped into any of the interfaces, and you can always communicate with it. The USB bus itself. So what's important to know is that USB is a host-controlled bus. Nothing on the bus can happen without host first initiating it. So there is no interrupts, there is no communication between 2 devices. There is always a communication between host and one of the devices. USB is a pooled bus, which means that host always asks the device for data, whether it wants to send it or receive it. But it's always the host who will initiate the communication. So how does the typical communication flow looks like? So at the link layer, which means that we are talking about the lower layer than our USB drivers operate, the in transaction, which means transferring data from host to the device, goes as follows. So the host issues the in token to the device. And then the device can decide whether it has the data or it is not ready yet. So if the device has the data, it will simply reply with the data packet. If it doesn't, it will simply issue a NAC to the host. And based on the choice made by the device, host will either retry the same packet or go and do some further processing. If we are talking about the out transactions, then it means that host is going to first issue the out token, then we send the data packet immediately without waiting for any communication from the device, and then the device simply answers ACK or NAC, whether it was ready to receive that data or not. The important improvement made in USB 2.0 is that after a single run of that schema, a host can issue ping and not yet may issue ping packet instead of sending the data packet. What's the difference, you would think? So the ping packet is like 8 bytes exactly, and the data packet is like 500 bytes. So it uses way more time on the bus, and the bus is blocked and you cannot communicate with any other device. So operating a transfer layer is very inconvenient because you can transfer only a very small amount of data. So that's why our drivers in the Linux kernel, our libusb applications, they operate at transfer layers. And the transfer is a set of consecutive transactions, and every of them can handle a couple hundreds of bytes. But a transfer may be really large. So a transfer ends with a short transaction or with so-called zero-length packet, depending whether your amount of data can be divided with endpoint size or not. So how do we operate with USB transaction in our Linux kernel? So the very basic structure that describes a USB transfer is a USB request block. It's basically an envelope for data that you would like to send or receive from the device. What you need to do is to just put the device, put the endpoint number, and then just schedule the envelope, give it to the mailman, and ask for and wait for a completion. So a typical life cycle of URB is to allocate it whenever the driver is bound to the device. You just allocate a bunch of URBs, and then you submit them based on the requests from the users. After the URB is submitted, then you have a couple of options what can happen. So basically, you may have an error. Then the URB is going to end with a failure, and you will get the status information over here. Or it can succeed, or you may decide that you are no longer willing to wait for this URB to complete, so just kill the URB, and that's all, you're fine. So how we can sniff the traffic between USB device and USB host? So the first option, which is the easiest one, because it's free, it's already there. I expect that if you are running Linux, then it is already in your system. So it's called the USB monitor. And the USB monitor is just a fancy name for a logger for the URB related events. So whenever a URB is submitted by any of the drivers, then this event is being logged to a circular buffer inside the kernel. This means that there may be a user space application that is waiting for those events and simply read them from the Linux kernel and present them to the user. There are two interfaces. One of them is binary, and second one is text interface. But fortunately, apart from that, we have an awesome application called Wireshark that can interpret both of those interfaces and just present the data to the user in a very user-friendly form. What's important to notice here is that because we are operating here at URB level, it means that we are not going to see the link layer packets that we've been talking about in the beginning. I mean the in token, out token, data packet, and stuff like that. We are going to see only a whole USB transfers. Another important thing to notice is that because URB is only an envelope for data, depending on the direction of the request, you need to check for data in different places. So basically, if URB is meant to be sent from device to the host, then you need to check the data at submit event. If the URB is sent from device, if the transfer direction is from device to the host, then you need to check for a data in complete event. Because whenever you are issuing the URB, the envelope may be empty, right? So our good old friend Wireshark. So what do we need to do if you would like to sniff for some traffic? So what I have here is just a USB mouse, like a standard one. And let's try to see what happens. Okay, we need wire, maybe first. Okay. Is it better now? Okay. So the first step that you need to do is you need to load a special kernel module called usbmon. You're done. After you load this module, you will get a number of usbmon devices in your dev directory. There are some numbers associated with that. It is usbmon 1, 2, 3, 4, 5, etc. And those numbers match with the bus numbers that you have on a host. So you probably ask, what the hell is bus number? So a bus number is a magical number that is added by the kernel to every bus that is registered on your host. So for every USB controller, there is a bus dedicated. It is independent from other buses. And you just need to use the correct one. So how to identify the correct one? So after you connect your USB device to your computer, you can execute lsusb. And now let's see the diff. Okay, here is the one. This is the Logitech. It's bus 1. As you see, I have 4 buses. because laptops tend to have some internal buses that are not exported outside, but used for camera or touchpad or keyboard and stuff like that. So now let's try to sniff what this mouse is doing. We just run Wireshark. We choose to listen at interface called usbmon1 and run it. So as you see, there is no much data traffic now, but if I start moving the mouse, we've got interrupt transfers coming in. So if I stop this, let's try to check. The important thing for you is the part over here. This is the leftover captured data. So basically, this is the stuff in the beginning is what a typical dissector in Wireshark for the USB protocol managed to parse. And the leftover data is the interesting data which is actually transferred within a protocol that you are using. If we use here, for example, the mass storage device, also the mass storage protocol would get dissected because Wireshark has a built-in support for some of the USB protocols. Okay. So usbmon is really nice tool and it is free and available everywhere. Unfortunately, it is not the perfect one. Because it is only a passive logger, it do not allow you to modify the data that is sent between the driver and the device. Why you may want to do that? Well, you know, there are some crazy people that are trying to exploit the USB devices or the USB drivers. That's one reason, and there is a whole bunch of people that are doing a really great job of rewriting some proprietary drivers to the open source one, and I really strongly support them. And sometimes there are cases that they need to modify the bunch of data that is sent by the driver. So for that purpose, you can use the USBProxy. It's maybe not the best piece of software that you can imagine. It definitely needs some more love. And currently, it works only on BeagleBone Black with some custom kernel image. But basically what it does, it uses the libusb, which is the library which allows you to communicate with USB devices from the user space, and uses gadgetfs, and simply does a translation and some mangling in between of those two interfaces, or whatever you ask it to do. So basically you can intercept the traffic between host and a single device. This is important limitation, only a single device. And you can do whatever you want with that traffic. You can drop packet, you can inject packet, basically all you want. The example that you can see here comes from my article where I created a proxy for ADB communication. You know, the ADB protocol from the Android device. So I created a proxy for it that allowed you to insert some shell commands or try to steal the key from the host and things like that. Okay, I need to, if disconnected, it works better. So probably one of the ideas when we are talking about sniffing the USB traffic is just, why don't we just use a logic analyzer? So definitely you can do that, but only for full and low speed devices. If we are talking about the high speed transmission, it has like 480 megabits. So you would need a really, really good logic analyzer to be able to handle that amount of data with such frequency. That's why OpenVizsla project has been created. And basically the whole idea behind that project is to use the USB PHY, the USB 3343, which will do the physical layer translation and then just return the ULPI protocol to the FPGA where you can do some processing and stuff like that and store it in a memory. And then you just use the FTDI chip to forward it to the host device. So you can basically passively listen for all the traffic on a USB bus. So a short demo. What we can choose? So the hardware is only one piece of the project. Apart from that piece, we have a software. Unfortunately, hardware is there and it works, but the software is not really so fancy. So the very basic control tool is the OVCTL, which allows you to get all the USB traffic in a text form. There is a new project started by Kate Temkin, ViewSB, which is an attempt to implement open source, let's say, UI for analyzing communication protocols. Unfortunately, it's in a very initial state. It doesn't work so well. So I do not recommend it for now, maybe in the future. And we have our good old friend Wireshark. So in the beginning, there was only a support for dissecting the USB link layer protocol. But one of my students in his degree or in his thesis created some extensions to the Wireshark and additional dissectors. So now if Wireshark supports dissecting of this protocol like mass storage, then you are able to get the traffic at the link layer, see the traffic at the USB transfer layer, and then pass it also to higher level dissectors and see what's happening there. Apart from that, I added also the capability of using OpenVizsla as external capture, so you can start and stop everything from the Wireshark interface. Unfortunately, all the stuff is not mainlined yet, but it is available on GitHub. There should be a link somewhere in the end of the talk, but we are in the process of mainlining those changes, so I expect that maybe in a year or something, you will be able to use OpenVizsla right from Debian or Ubuntu or whatever are you using. Okay, so short demo. Try to remember what we have here. You just see the... Okay. Can we increase the font zoom? Okay. Yep. Okay, so what you can see here is that we have only information that USB interrupt in transfer has been finished. And we have some data received from the device, right? You don't see any kind of tokens here. If we go now to OpenVizsla, okay, let's connect this. First of all, the difference is that apart from the usbmon interfaces, we have also OpenVizsla interface. Then you just open the settings, you choose at which speed you would like to sniff the traffic, and just hit start. Okay, now I will connect the mouse to the computer. So what you saw in the beginning was the enumeration process. And now as you see, that even though I'm not moving the mouse at all, the data, maybe let's make it more visible. The frame numbers are constantly increasing. And the reason for that is that we are not only sniffing the USB transfers, but we are also sniffing the USB tokens and transactions. So if I start moving my mouse, you will see also the data packets. And now what we see here is that the host was issuing an in token, so it was asking the USB mouse for the data, and the device was responding, I'm not ready to provide you any of the data. But if we go a little bit higher, you will see that when I started moving my mouse, then we have an in token for requesting the data, we have the data sent by the mouse, and we have acknowledged from the host that the data has been received. Okay, that would be all for OpenVizsla. Now let's go to some more fancy stuff. So having the ability to sniff the traffic or to modify the traffic is really nice if you're a developer. But what if you are a security engineer and you say that okay, I have a server, or maybe I have some edge computing device that is left in the room unattended. It's maybe not very well secured in terms of physical access, so someone may just come there and plug in the USB stick. One of the famous attacks related to the USB was related to ATMs. So You may be not aware of that, but ATMs indeed have USB connectivity. You just need to break a piece of plastic or cut in a hole in a metal cover, and you will be able to plug in literally anything that you want. So now it's only, you need to know the method how to access the operating system and exploit it. Another famous exploit for the USB was PlayStation jailbreaking. There was a vulnerability in the USB stack, so if you connect a specially crafted USB device, you could get a full access to the console operating system. So the first hardware that has been developed for that purpose was a phase dancer. And the reason why people started developing that is because laptops like this one or PCs, they usually do not have the USB device controller. So what they came up with is that they connected FTDI chip with USB 5 and the microcontroller and simply drive it from the one side to create a USB traffic from the other side. So it's basically a UDC-like device. And for that device, they developed a special software stack that allows you to implement any of the USB devices in a Python framework. By the way, if you use two of those devices, then you can do a proper man in the middle with intercepting the traffic on your computer, because this device is so awesome that it's capable of not only acting as a USB device, but it can also act as a USB host. Unfortunately, that device has also disadvantages, and the main disadvantage is that it supports only low speed, and it is really, really slow. So if you like to do any kind of effective fuzzing, then you have to go for something better. And one of the options is a GreatFET. Initially, it was a platform developed to interact with HackRF radio hacking solutions. But then they realized that this fancy chip that they used here from the NXP, it has two USB controllers. Unfortunately, only one of them is high speed. But still, full speed is way better than low speed, so you will get some performance improvement. This board is backward compatible with the previous one, so you can use the same Python stack and run the same scripts to test. You'll just get better results in terms of performance. An interesting project related to that board is GreatFET Rhodadendron, which is basically an add-on board for the board that you have seen on a previous slide, which used pretty much the same setup as we had in OpenVizsla. So it even utilized the same USB 5 to capture the traffic. So this makes your GreatFET act as a USB sniffer and allows you to capture the traffic. Unfortunately, there is no memory built into GreatFET board. So in OpenVizsla, we have 100 megabytes of buffer. Here we have 0 or maybe a couple of hundreds of kilobytes inside the chip itself. So you're not going to be able to sniff some fast devices that send a lot of data. A software tool related to the two previous boards that I mentioned is the UMAP 2. UMAP is basically a Python framework that is used to do some USB fuzzing, emulation, scanning. Basically, it's a very nice tool for all penetration testers and security engineers. So the UMAP scan allows you to enumerate all the drivers that are available on a particular host that you connected with, so you can do a really good reconnaissance. Then you can emulate any of the USB devices that you want from Python. UMAP 2 allows you to grab stages of what are stages? So stages are basically the way how the driver on a host interacts with a USB device. Based on those stages, you can do some modification-based fuzzing and take those stages and the USB device emulation and then try to send some not so random packets to the host that will try to exploit the USB driver on a host. There are 3 backends supported by this tool. Phase Dancer and GreatFET that we've been talking about. There is Rasp Dancer, which is basically a hat for Raspberry Pi 2 with a USB 5 that serves the same purpose as a Phase Dancer. And there is a GadgetFS, but GadgetFS backend is very limited because kernel does some sanity checks on a packet that comes from the user space. So you cannot get such good effects as with those custom boards. Another interesting approach to testing USB stack security is virtual USB fuzzer, which is basically the idea to use a hypervisor like QEMU here, and most of those hypervisors allows you to redirect the USB device from host machine to the guest machine, right? So the idea is that instead of passing the exact USB device from the host, you just emulate one in the software. And you simply use the same protocol to act as any random USB device. The advantage of such approach is that you can run any number of QEMU instances that you want depending on your hardware capabilities and make your fuzzing parallel and way, way faster. Unfortunately, because you are bound to QEMU protocol, it means that you have also some sanity checks and you're not going to be able to generate all the kind of traffic that you may want to. Yet another approach is to use the syscaller. How many of you is familiar with syscaller fuzzer? Okay, so not so many. Basically, the idea for syscaller is that it's a fuzzer that allows you to pen test the Linux, maybe not pen test, but test the Linux kernel security based on scripts that describe how to call a specific syscall. So basically, it's a fuzzer that calls syscalls based on some abstraction layers provided for those syscalls. And the idea here is to use dummy HCD, which is a kind of USB loopback device, and issue a syscalls at the gadget side. So use custom module or gadgetfs to issue a syscall at the gadget side that will appear and test the USB host stack. I mean the USB host side of the stack at the same machine. So what's the issue of this approach? Basically, you're testing the machine on which you are actually sitting, and you go through whole USB gadget stack, which means that you have to pass some sanity checks and stuff like that. The advantage of this solution is that it can easily be run in a cloud without modifying any hypervisors or anything like that. So you can use Google Cloud and just run it. And it is really fast compared to all other solutions. Okay, so summary. Basically, I believe that I managed to show you that there is no dragons in the USB protocol, and if you really need to debug something or try to write your own driver, then there is plenty of hardware, of open source hardware that you can use, and you don't need to spend a lot of money to buy a custom solutions. I mean custom, commercially supported. So basically for everything that I show you, there are some proprietary products in a while that you can buy for a large amount of money. But I believe that at least 90% of use cases can be fulfilled with the open source and open hardware tools that are available and are way cheaper than the commercial one. In the end, I would like to mention that I believe that there is no perfect architecture for the USB security, for the USB security testing. Based on my experience, not all of the issues can be triggered with the fuzzers like syscaller or the VUSBF, because they still need to pass some sanity checks. So if you really want to test the security of some USB host, then you should probably have some mixed solution and do some farming using syscaller or VUSBF first, and then try to explore a little bit more some of the use cases with the physical devices connected to that particular host. Okay, that would be all from my side. If you have any questions, I will be happy to answer.
Thank you very much. Okay, questions?
Thank you so much. So I have a question about OpenVizsla hardware performance. Do you have numbers of this FPGA hardware? Is it possible Is it available to measure or take data from high-speed devices?
Yes, yes, it's definitely possible. Actually, if I'm to be honest, I didn't manage to saturate the performance of FPGA itself. The only limitation that I came up with is the limitation of the speed of this FTDI chip. So basically you have the USB PHY, then the data is being parsed by the FPGA and stored into the memory. And that part is really fast. But then you have the FTDI chip that has to communicate through FPGA and read the memory and return it to the host. And this is actually where I expect OpenVizsla to have a bottleneck. Still, it is way enough to sniff any of the mobile phones that I have, any of UDC capable single board computers like Odroid, Raspberry Pi Zero, and stuff like that. So it's definitely, the performance is good enough to sniff a single devices like this one.
Thank you. And Chris, you have to pick up the best question for our gift to be at the end, next one.
Okay.
Hi again. I think you know what I'm going to ask. First of all, one small comment / question. I guess everything you just told is not related anymore to USB 4.
Yes.
And the question regarding your presentation, OpenMon and OpenVizsla, usbmon and OpenVizsla, they're using Netlink protocol, right, to communicate with Wireshark?
Nope. So the Netlink is used only by Wireshark for the usbmon. But in terms of OpenVizsla, it is just the libusb program and a pipe between two processes.
And what is performance of this solution? Wouldn't it be better to use Netlink?
I don't think so, and I don't see any way how you could use their Netlink, because basically OpenVizsla is a custom USB device, so it doesn't have any driver inside the kernel, and you are driving everything from the user space using libusb asynchronous transfers. So it definitely, there is no bottleneck, because there is triple buffering at least. So you're submitting number of buffers and just waiting for a completion. And in terms of performance of communication between Wireshark and the daemon that is listening for the OpenVizsla, it's just the standard Wireshark limitation and inter-process communication. I believe that this is still way more than the communication at the USB side.
Thank you. The next question.
Thank you very much. What about USB version 3 and which devices is available for this kind of protocol? And the next, could you expand your experience about which level of device speed is the limit of using software sniffing like usbmon? Thank you.
Okay, so for usbmon, there is I never hit the limit of that. Even if the device sends a pretty large amount of data, you can always increase the internal buffer size in the Linux kernel, and then you should be able to grab the data fast enough. If you are speaking about support for the USB 3.0, then usbmon is capable of doing that, because it operates only on URBs, and the URBs are pretty much the same for all versions of the USB. If we are talking about the OpenVizsla and the GreatFET Rhodadendron, I never can remember that name. So both of them can support only high-speed USB. There is no open hardware tool that I'm aware of that can support USB 3.0. And the main reason for that is I expect that the FPGA that would need to do the actual dissecting would be pretty expensive.
Okay. Thank you. I think that we have time for the last one.
I have a question about OpenVizsla. You told that it's an open hardware project and the FPGA on board. We can use, maybe you know that we can create the stream for that FPGA and use OpenVizsla as a fuzzer to generate maybe fastest to generate a lot of packets and speed up fuzzing.
So the answer is not so simple. Basically, if you take into account only a basic version of OpenVizsla like I have here, it's not possible to generate any USB traffic. Basically, the USB PHY, which is soldered on the board, it is set in a mode that it is only passively sniffing the traffic that goes through the OpenVizsla. If you take a look at the board, you will see that I have here a connection to the host, and here I have a connection to the device. And here I have a third connection that communicates with the FPGA. So basically, there is no hardware sitting in between of those two connectors. There is only a passive sniffing. So you cannot modify anything. But OpenVizsla has a couple of free pins, and I managed to create an add-on board, some extension for the OpenVizsla that allows the FPGA to drive the USB PHY and generate some packets. So that idea can work, but you need to develop some hardware extensions for the OpenVizsla. But then, indeed, it is even better than all the fuzzers that I mentioned, because it allows you to generate a USB link layer tokens, not only the USB transactions sent by some UDC or some controller embedded onto the board.
Okay. Thank you, and thank you very much for your presentation.
Thank you. If you need some links or something, they are all in the end of the slides.
Thank you. So we have a short break, 10 minutes break, and next will be a talk from Elena Geshtova about Linux security.